of composite function about convexity. Okay. So here we take example, and that example is okay. Suppose if there are a function, and we say that function is defined by, and we call that function is a maximum function. Okay. So maximum function, and that function is defined such that fx is equals to maximum of this x1, x2 up to xn, where these x1, xn are the components of your x vector. Okay, so this fx, where x be the n dimension, this belongs to Rn. So this function is defined as maximum of suppose which component is maximum, suppose x1, x2 up to xn. Okay, suppose for example any function whose if we take in any x, and that is x belongs to R3 and component is 1, 2, 3, then what are the function of fx? That equals to 3, because 1, 2, 3, the 3, 1 is the maximum. Okay, so this maximum function you have to check this is a convex function or not. So this is convex in your Rn. Okay, so here what is about x? X is belongs to Rn here. X is belongs to Rn, and this means x is simply the components of x1, x2 to xn transpose, because this is column vector. Okay, so if we apply this fx, so this is equals to maximum of this thing. Okay, and suppose if two components or three components are same, suppose there are the vectors, suppose 1, 1, 3, 3, 5, 5, 6, 7, 8, 9. Okay, and 10, 10, 10. Okay, so this is the component of the vector x. Then maximum of that, that equals to of course 10. Okay, because this repeated 1 times, 2 times, 3 times, or infinite time. Okay, so which one is maximum? This is your function fx. Okay, so to prove that this function is convex or not, so for that we have to solve this and take this function is convexity. For convexity, we take any theta which lies between 0 and 1, and when we try to prove that f of this theta of x1 and theta of suppose y, if x and y are two components of that uh, function. Okay, so here if we choose the function, and we take this function fx in short form, we take the maximum value of this xi, the maximum of xi, where I is varies from 1 to n. Okay, and this satisfies for this theta, which is lies between 0 and 1. Okay, so if we take any 2 points, suppose x and y, it belongs to this Rn. Okay, so if we assume 2 points, suppose x and y, and that belongs to your Rn component. Okay, so then what about the uh, Cornish combination of this image? Image means theta of x plus 1 minus theta of y. So this equals to basically this maximum of all I, that is I is varies from 1 to 1. This is this function. So this function, the point is theta of x plus 1 minus theta I. Okay, so this means you have like this in the form of this theta of xi and plus 1 minus theta of yi, because the components of x is here x has x1, x2 to xn component, and y has y1, y2 to yn component. Okay, so maximum of this, so you can write this term as if we take the addition of maximum taking, or we take maximum of this and maximum of this and then add it together. Okay, so that term is always greater than or equals to when all these terms are same. So this equals to maximum of taking this theta of xi and plus maximum of this I from 1 minus theta yi. Okay, so because uh, y, if we take suppose uh, xi has suppose component 1, 2, 3, okay, and yi suppose your component is 2, 3, 4, okay. So if we adding x1 and x2, okay, so what are the component of this is 3 and 5 and this is 7. Okay, so here if we take 3, 4 and 1 here. Okay, so here the component is 3, here this is 5 and this is the maximum is here, this is 3 and 4. Okay, so sum of xi plus yi equals to, this equals to 3, 5 and 4. Okay, and maximum of this, maximum of this xi plus yi, this equals to 5 here. Okay, and if we take maximum of this, so maximum of xi, this equals to 3 here, and maximum of yi, this equals to 3. And if we adding separately these two, this becomes 6. So this is, if we adding separately, this is greater than, okay, than this thing. So this is greater than, okay, this thing. Or in some cases, this is maybe equal. If we taking 2, 3, 4 here, if we taking 2, 3, 4, then maximum is if we taking another vector, suppose zi, if we taking 2, 3, and 4, in that sense, the maximum of this is maximum of zi that equals to 4 here. Okay, and adding these two, this is maximum of this is 3 and this is 4, this becomes 7 here. Okay, and if we adding these two, this is zi xi, this is 3, 5 and 7. Okay, so here the maximum of xi plus zi, this is also equals to 7. So this either equals to this term or this is greater than. That's why we can write here this is greater or equals to, separately we can add in this. Okay, so now because this theta with a scalar one, so you can write this in the form of theta with a maximum of xi or maximum of I varies from 1 to n of xi plus here 1 minus theta of maximum of this term over I is varies from 1 to n of yi. Okay, and what is the function of maximum of xi? Maximum of xi defined by fx. So this equals to theta of this function fx, and here 1 minus theta, and similarly this is the yi component. This function is y because x and y vary from I. Okay, so you can write this thing. This is the image of this honest combination of these 2 points, 1 minus theta of y. This is less or equals to theta of fx plus 1 minus theta of fy. So you can write here the function f is convex. Okay, so your function f is convex in the domain R. If it is convex over R. Okay, so this is a simple proof. Okay. So now, if we take another example and write any function of fxy, fxy, and this function is defined by like that, x square over y. Okay, and this function is known as quadratic over linear function. Okay, this is quadratic over linear function. So any function which is quadratic over linear function is always convex function, provided that this denominator term is non-zero. This is always convex when this y is greater than 0. Okay, so this function is always convex. Okay. So you have to check this is convex or not. So here you find simple, you find the Hessian of that matrix, and if the Hessian is greater or equal to 0, then this function is convex. Okay, so this means you have to obtain the Hessian of this function fxy, and this Hessian is defined by this fxy, and this equals to second derivative of this fxy, and this is here yx, and this is y. So you solve this and try to find what are the values for this function fxy. Okay, so if we differentiate 2 times, so this becomes 2x, and then again this is 2 by y, this becomes 2 by y. Then setting here 2x over y and then y minus 2x over y square. Okay, and similarly then y and then x will become minus 2y to this x square, and then differentiate this with respect to y 2 times, so minus 1 by y square and then minus 2 y cube. This becomes minus minus plus, this becomes 2x square by y cube. Okay. And we solve this if we're taking 2 over y cube outside from this interval, it becomes y square, this is xy, this is minus of xy, and this is x square. And then also write this equals to 2 over y cube, and this is y, this is y square, this is y square. So this becomes y minus x and y minus x transpose. Okay, so here y is greater than 0. That's why this term is always greater or equals to 0. Okay, so therefore you find the Hessian is greater or equal to 0. So this implies the function of xy is convex. This is convex function. Okay, or you can observe that here this determinant is 2x square by the power of 4 minus and minus plus 4x square by the power of 4, and here for any value of x, and y, okay, y is non-zero, so this is always uh, greater than 0. Okay, so that's why this term is greater than 0, and for that x, that because this x is lie between r, for that x which is equals to 0, this determinant of that equals to 0. So that's why Hessian is either greater than 0 or equals to 0 for all x which belongs to minus infinity to infinity, and for any positive value of 1. Okay. So similarly, you can also define another function which is known as log sum exponential function, and this function is also convex. So if we define any function fx, that equals to log of exponential of x1 component, exponential of 2 component, and similarly exponential of nth component of x. So this function is basically known as, this function is known by log sum exponential function, and this function is convex. Okay, so this is convex. So convex because if you find the second computer of this fx, this is always greater or equals to 0 for all x which belongs to the f. Okay. So you take this and try to solve this is convex or not. Okay. So next page, we define two special type of function, and that is a graph of a function. Next page, we define epigraph and hypergraph. epigraph. So the graph of function, the graph of function, and that function is defined like this: r into r is defined as collection of all x, this is the ordered pair x, and the corresponding image of that. Okay, so x and fx, this ordered pair such that your x is belonging to the domain of that function f. Okay, so this is basically this function is from Rn to R. So here x is your n dimension and fx is your one dimension. Okay, so this means x is n dimension. This belongs to this belongs to Rn due to this function is from Rn to R, and this fx is belonging to R. So this means and this is the order pair of Rn and R. So that's why this is basically subset of, so which is a subset of R n plus one dimension, because this is n dimension, this is one dimension, so this is R n plus one dimension. Okay, so you can visualize this graph uh, in, if we take in R2 plane. Okay, so the epigraph of a function, simple function with one dimension, or you take this Rn to R. This is defined as this is defined in basically you can visualize this in this space Rn plus one dimension. So if we take simple, if we take this one dimension is R to R mapping. If we take R to R mapping, then the image of that is R2 plane. Okay, so here if we take this R2 plane, R2 plane, we're taking R2 plane here, and your graph is suppose any corresponding to x here. This is your x, and corresponding to your suppose this is your fx. Okay, so this function is basically R to R. Okay, so your epigraph is basically one more dimension than your this function. So this is one dimension. So your epigraph is of two dimension. So this is basically defined by the formula, and that formula is defined as this Rn1 defined as this epigraph means ep of f. This is equals to collection of all ordered pair x and t, such that your x is belonging to domain of function, and your fx is less or equals to t. This is the definition, and which is whose subset of which is a subset of R plus one dimension. Okay, this is Rn plus one dimension. Okay, so here collection of all x, your all x. Okay, and here your fx is something less or equals to t here. Okay, so this is your वो सारे x हमारे ये हो गए, सारे x मींस ये, तो fx क्या होगा, यह हमारा this is your fx. Okay, so this has any finite value, and this is less than or equals to t. Okay, so this means for any t. Okay, so this means this portion is the collection of all x and fx, which is either equals to means we take this line, that line is fx, greater than that values, and that value is t, any real number. Okay, so you get that reason. You get that reason. Okay, so this is your EP of F. So this is EP of F. Okay, so this is your epigraph of F. Okay. Similarly, you defined basically this word EP. EP means what is the meaning of EP? EP means above. So you can also relate this above graph means which graph you are plotting. The above portion is known as EP graph. So EP means above. So that's why uh, uh, that portion of graph is known as EP graph. Similarly, you can define the hypograph. Okay, so here this epigraph, we say that this function we have no idea about this function fx. Okay, so here we make this curve as randomly like this. Okay, so here we by using this epigraph concept we define or we can uh, say that this function is convex or not. Okay, so for that you say that a function is this function is convex. If this function is convex, if and only if the epigraph means this epigraph is your convex set. If the epigraph is your convex set, means this region is your convex set, then this graph, this function is your convex function. Okay. So here we write this thing, this remark as a function is convex. A function is convex if and only if its epigraph is a convex set. Okay, so this means if we take any function and that function is suppose defined like this. Okay, for this reason. Okay, or any reason. So if we take this function in the first quadrant like this. Okay, this is your function f, and here we define the epigraph, and the epigraph is the region that is above that function. Okay, that is your epigraph. That is your epigraph. Okay. So here this remark say that this this region, if this region is convex, okay, so if we join any two point and this line segment is completely lies that interval, so this means your this function, this region is your convex set, and if this region is convex set, then this function f is must be convex. Okay, तो आप ये देखिए ना कि यहाँ दो हम पॉइंट अगर हम पॉइंट करें, that straight line always above that. Okay, so this means if EP of f is convex set, then your function is convex function. Okay. So similarly, we can define hypograph. So here, similarly, function is concave. Function is concave if and only if its hypograph is convex set. Is a convex set. Okay. What is the hypograph? The hypograph की definition क्या है? तो hypograph of f means hypo of f. You can define the collection of all xt such that x belongs to domain of f and your function fx is greater or equals to t. Okay. This is your hypograph. Hypograph means if this is the reason, okay, and function is x, and corresponding function is this is your fx. Okay, then what is the hypograph? Hypograph is limit curve. This region is set to hypo outer. This is hypo outer. Okay, so this says that if the region if the region is convex, if the hypograph is convex, okay, the hypograph is convex. This means you if you take this type of function, okay, and here the hypograph is this region is hypograph, this region is hypograph. Okay, so this is hypo of f, and this is a function fx. And, okay, so this says that if hypograph is convex set, if we one two line two different point on that set, this line completely on that set. So this means this hypograph is convex set. If this hypograph is convex set, then this curve is your this is your concave function fx. Okay, and here if this is convex set, then this function is convex function. Okay, so depending on epigraph and hypograph, if this epigraph and hypograph sets are convex set, then we can easily define that the function is convex function and concave function respectively. Okay, so now next one is if we take the two functions, okay, and if we impose some certain conditions on that functions, then we are able to uh, define what are the composition of that function and what nature of the composite function. Okay, so page, next page, we define composition function. Composition function. So if we take two functions, suppose one is h, and this function is from we take simple R to R, simple function. Okay, and another function is suppose g, it is also from R to R. Okay, then what about the composite function that is f, and that function f is h of g, and that is also from R to R, and that function is defined by this function is defined by uh, this type function. So this is the function suppose in x, and this operate here g function. This is the image of gx, and then we define this h function. Okay, so this is your h of dx. Okay, and this function f, this is basically composite function. Okay, so what are fx is? So fx is h of gx, so h of gx. Okay, so what are the domain of this function? The domain of f, or we can write simply d of f, domain of f. This is the collection of all x that belongs to domain of g, such that your gx is belonging to domain of h. This is belonging to domain of H. Okay, so this is your domain of F. Okay, and if we try to find what are the second derivative or derivative of that function, okay, so, okay, so here uh, your fx is equals to h of gx. Okay, so okay, so the second derivative, the second derivative of this function is equals to. So if we are interested to find the second derivative of the composition function is h of g. Okay, so f double prime x, this equals to, if we uh, with this function into this function, so we're using product rule here. So this equals to h of double prime of this function e prime x, and if we again prime of this gx, and here we differentiate this thing. This is g double prime x. Okay, so this is the composition of these two functions. Okay, so you can find the of this f double prime. Okay, so f double prime is defined as g h double prime gx into g dash x square, and h prime x h prime g and g double h double prime of function dx into g dash x square, first term, and then second h dash of this gx with g double prime of x. So this is your f double dash s. Suppose this is equation star. This is your main equation. Okay. So also you know that the main function is convex. So for convexity, so convexity, convexity of f implies implies you this function f double prime in second derivative is either greater than 0 or equals to 0. Okay. So this means if this function is convex, if this satisfies this condition. Okay. So ये कंडीशन हमारी कब सेटिस्फाई करेगी, यहाँ पे अगर आप देखें तो अब इन दो टर्म्स का सम है, if both terms is equals to greater or equals to 0, then the sum is also greater or equals to 0. So here we take some cases, and there arises the four cases. Okay, so here we suppose that ओके, तो अभी हम 10 मिनट बाद लेक्चर लेंगे। हाँ, तो इसके आगे हम 10 मिनट बाद ज्वाइन। Basically this function g, and g is convex. So suppose this g is convex. If we take g is convex function, so this means you have taken this second derivative of this is greater than 0. Okay, and h is convex. So convex, and of course one more condition, this non-decreasing. So why we are choosing this condition? Because we are interested to find the value of this f double prime. Okay, so that's why we take in this condition. So here, if we take h is convex, this means double prime is greater or equals to 0, and non-decreasing means h prime is greater than 0, greater than or equals to 0. Okay, so here, look here, if this h double prime is greater or equals to 0, and whatever the value of this g prime, either positive or negative, the square of that is also positive. So multiplication of that two is always greater or equals to 0. Plus here, this h prime, we select here h prime is greater than 0 because that's why we take in the non-decreasing function. So this is positive, and g double prime x is also positive. In that sense, this whole term is positive one. So here you look here, this is basically this f double prime is the sum of two functions, and each functions are the product of two. Okay, so if we are interested to find this is greater than 0, so this is greater than or equals to 0, this is greater than or equals to 0, this is greater than or equals to 0 if and only if this term is positive, this term is positive, or this is negative, this is negative. Okay, similarly, these both are positive only when this is positive, or this is negative, this is negative. Similarly, for concave function means f double prime is less or equals to 0 if this term, product of these two terms is less or equals to 0, and product of these two terms is less or equals to 0. So here less or equals to 0 means the product of these two, either one is positive, another is negative, or this is negative, this is positive. Similarly, the product of these two is negative, either this is positive, this is negative, or this is positive and this is negative. Okay, so here the first condition is if we take this thing, so it follows that uh, your equation star question star, that your f of double prime is greater or equals to 0. Okay, so this means f is convex function. So f is convex function. Okay, so here there are some conditions depending on the signature of plus 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 minus 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 plus minus and minus plus. Okay, so there are basically four conditions are arises. So first one is that uh, this f is convex. This is which is I've already written in above line. So we summarize, this is f is convex function. F is convex if your composition function h is convex function. H is convex function and also non-decreasing and non-decreasing. Non-decreasing. And G is convex function. So if G is convex function, if G is convex function and H is convex and non-decreasing, so here your double prime is always greater or equal to 0, because here this is the product of these two. Similarly, you can write second one, and here we define greater than 0. So we take here, this is negative, so product of these two is always uh, positive. So this term is always positive because g prime x square. So either g is increasing or decreasing. This term is always positive here. So this is negative. Okay. So here this term is if we take this is negative, h is negative. So this product is always negative. So that's why here we take h is always greater equals to 0 for convexity. Okay. तो convex के लिए हमारा h जो है दोनों condition में h हमारा convex होना ही चाहिए. Okay, so here H is convex and non-decreasing. Why non-decreasing? Here we take this is positive one. Okay, and here G is if we taking this is G prime double prime is concave. If we take concave, this is less than 0. So that's why we take this is also less than 0. That's less than 0 means this is non-increasing. Okay. So here we take H is non-increasing. Here we take H is non-increasing, and G is concave. If this type of function, then the composite function f is always convex function, because this f is h is convex, so that's why this is greater than 0. What about the g has, because the square of that is positive 1, and non-increasing, this means this is less than 0, less or equal to 0, and g prime is concave, this is less or this is a non-increasing. Non-increasing means this is a you G is concave means this is negative. This is negative, and this is non-increasing means this is a negative. Negative and negative product of these two is positive. So that's why this term is positive. This term is positive. Similarly, for concave, so concave के लिए हम similar pattern लिख लें, और negative होने चाहिए. Negative के लिए product of either this positive, negative, positive, negative. Okay, or this is a negative, positive. So here F is concave. F is concave if H is concave and non-decreasing, and G is concave. Fourth one, F is concave concave होगा यदि H is concave and non-increasing, and G is convex. Okay. So here, this is the result of this theorem. Okay, and what are the result? Result is only based on this F double prime equals to H of double prime, of whatever the function gx, okay, into this g prime x square plus h prime, which is a function of gx here, multiplication g of double prime x. Okay, or you can say this is h double prime into g prime square plus h prime multiplication g double prime x. Okay. So here, this f double prime is greater or equals to 0. But this term is greater or equals to 0, and this term is greater or equals to 0. Okay, so this term is always greater or equals to 0. This means this is always convex. So for f is convex, this h is always convex. Okay, and here the product of these two is greater than or equals to 0. This means here if g is convex, then this is a non-decreasing function. This should be greater than 0. Both are negative one. This is concave and this is non-increasing. Similarly, for concave, this is less or equal to 0. And similarly, you see that this f is convex or concave. This is depend on the h is convex function or h is concave function. Additional requirement is this your g. Okay. So if you take some examples, which is depending on that composite function. So on next page, if we take some example here. Example is if the g is convex, if g is any convex function, then what about the exponential of gx? Okay, so if g be any convex function, then what about the exponential of that? The exponential of that is also convex. Okay. Is also convex function. Okay, so you have to check this by using the opposite function. And if g is concave, function, then logarithmic of gx is concave function. Okay, so and the result is if we take g is concave function and positive, then what about 1 over gx? 1 over gx is convex. If g is convex, non-negative, and we take any integer that is greater or equals to 1, then the gx to the power p is convex function. Similarly, there is one more result. This is J is convex, then you have checked what are the value of minus of log, minus of gx. This is convex. Okay, and this is convex on some domain here. So this domain is collection of all x such that your gx is -1, because that's why here this is not defined. Okay, so you take this thing. Okay, so you check this all results and try to solve those. Okay, so lastly, that if we take a simple problem and we ask you to check this function is convex or not. So if we consider the function, and suppose that function is gx, if we take, this is based on your composition function जो भी हमने कराई. Okay, so if you take gx equals to something x square with some domain, so if we take the domain of g is simply r. Okay. Okay, and other is if we take hx, okay, and hx equals to some another function. Suppose this is 0 with domain 0 ना लिख करके हम इसको कुछ और लिखते हैं. Suppose this hx equals to any constant. Suppose this equals to 5 with some domain of this equals to 1 to 2. Okay, so this gx is convex gx नहीं, हमें सिंपली हमें देखना कंपोजिट फंक्शन देखना है. ओके, so we have to check the function f. Okay. So then fx that equals to g h of g. Okay, this is convex or not? This is convex or not? Okay. So you have to check this. So this function is convex or not? If hx equals to x square and gx equals to x square and hx equals to 5, then you have to find the value of this function. We take 5. Oh, okay, 5x ले लेते हैं. 5x ले लेते हैं. Okay, so you have to take this value and you have to prove that this is convex or not. Okay, so this is convex or not. तो यहाँ पे अगर हम फाइंड करें इसका solution, you take here what is the value of f here. So here fx is basically h of gx. Okay, so this equals to h of what is the gx is x square. Okay, so h of x square. So what equals to h of x square? H of x square equals to 5 of x square. Okay, so this h of x square here, where we gx, here if we take gx equals to simply x square. So this is your convex function. This is your convex function. And here hx is 5x. 5x is straight line. A straight line means this is a fine. So this is also a convex function. This is also convex function because this is a fine. Okay. So the composition of each of this, if both are convex function, then composition is also convex. So here this f fx that equals to 5 of x square. So this is convex or not. So this is convex or not. Okay. So some students say that this function is convex because this is also a square function. This is your convex function because it's this is. But this convex function, yes, is convex function on your real R. Okay. And this hx is convex on those set 1 and 2. Okay. What about this? Because what are the domain of f? So domain of f is here domain of f, if this is a square function, x square, so domain of f is goes to this वो सारी values हमारी 1 2 पे जाए minus this interval and union this 1 comma root 2. This the interval where when you squaring this goes to here 1 2 point. Okay, so domain of f is this thing. Domain of this is this means your 0 is here, your 1 point is minus 1 is here, 1 is here, similar root 2 here, and minus root 2 here. So you take this interval and this interval. Okay, so and union of that. So this is not convex set because if we take any point, suppose if we take this point and this point, and if we line joining these two, so this whole line segment doesn't lie in this set. Okay, so that's why this set is not convex set. Okay, तो फंक्शन तो आपके जरूर कॉन्वेक्स दिख रहे हैं पर डिफाइंड है जिस डोमेन में वो हमारा कॉन्वेक्स सेट ही नहीं है, तो इसलिए हमारा जो फंक्शन है वो मेरा कॉन्वेक्स फंक्शन नहीं होगा. सो दिस इम्प्लाइज आवर fx is not convex function. This is not convex function. तो सिमिलरली आप ऐसे ही चेक करेंगे, पहले आप डोमेन देख लेंगे, उसके बाद फिर उस प्रॉब्लम को आप सॉल्व करेंगे. तो ठीक है, आज इतना ही करते हैं. अभी थोड़ा सा काम आ गया है हमारे पास, तो आज के लिए इतना ही करते हैं, फिर हम नेक्स्ट क्लास में हम करेंगे. ओके, तो आज इतना ही करते हैं, बाद में नेक्स्ट थर्सडे फिर. ओके, थैंक यू.
Thank you, sir.
थैंक यू. आगे की क्लास दूसरी नहीं लेंगे, थोड़ा कुछ इम्पोर्टेंट वर्क आ गया है, तो आज इतना.